Relation between line currents and phase currents in case of a balanced delta connected load. Here you can see that a balanced delta connected load is connected across a balanced three-phase system of voltages. Here balanced load means loads connected between all the phases will be same. Here you can see that ZAB, ZBC and ZCA will be equal in magnitude as well as in phase. And as we have seen in the case of a three-phase balanced system following ABC sequence or RYB sequence. Here in this example I have taken it as ABC sequence. So in case of an ABC sequence, you can see that VAN, if you are taking VAN as reference, it can be represented as VP angle 0, where VP is the magnitude of the phase to neutral voltage, and in that case VBN will also be equal in terms of magnitude, but it will be displaced by an angle of minus 120 degree. That means VBN will be lagging with respect to VAN by 120 degree, and VCN will be lagging with respect to VAN by an angle of 240 degree. So it can be either represented as VCN is equal to VP angle minus 240 degree, or it will be equal to VP angle plus 120 degree. And we have seen that in case of a balanced three-phase load, the line voltages VAB will be given by root 3 into the phase voltage angle 30 degree. That means if you take root 3 VPS as the magnitude of the line-to-line voltage, it will be equal to, say, it can be represented as VAB in this case. Here you can see that VAB, the potential of A with respect to B. That means the voltage available between these 2 points will be equal to VAB, which is given by root 3 PS. Root 3 VPS means root 3 into the phase voltage. This VPS will be the same as the magnitude VP here. But you can see that if you consider this as the reference phasor, this will be leading 30 degree with respect to this phase. So the balanced line to line voltages can be represented as VAB is equal to root 3 VPS angle 30 degree, and VBC will be equal to root 3 VPS. That means all these voltages are equal in magnitude but are separated by an angle of 120 degree each. Here you can see that this will be leading with respect to the reference phasor, which is VAN by 30 degree, and this second volt VBC will be lagging with respect to VAB by an angle of 120 degree. So it can be represented as root 3 VPS angle minus 90 degree. Similarly, VCA is equal to, this is line to line voltage angle minus 210 degrees. This derivation we have already seen from the previous lectures. And here in this case you can see that the line voltages, if you consider the voltage across each branch of the balanced delta connected load, you can see that the voltage across the impedance will be the line to line voltage. Here you can see that this impedance Z delta or the ZAB is connected between these 2 points. That means the potential across this load or this branch of the load is VAB. Because of that, a current will be flowing through the impedance, which is indicated as IAB in this direction. And you can see that if you have a potential difference between these 2 points, AB given by VAB, the current flowing through the impedance connected between those 2 points will be equal to VAB divided by the impedance connected between, or the impedance in the branch. So here you can see that IAB will be equal to VAB by Z delta. Similarly, IBC will be equal to VBC by Z delta, because here you can see that IBC, here the voltage between these 2 points are VBC. That divided by Z delta will give you IBC. Similarly, ICA, current flowing or current indicator like this. Here you can see that the potential or the voltage between these 2 points is VCA. And in VCA you can see that C is at a higher potential, so the current will be flowing in this direction. So magnitude wise, or if you represent all these quantities in complex form or in the vector form, you will be getting the complex form of the currents ICA. So if this is a vector quantity or phasor and this is represented as a complex quantity, ICA will be obtained as a phasor or a complex quantity. And by this way you can calculate the current in each phase of the delta connected load. Another method to calculate the phase current is to apply Kirchhoff's voltage law equation to different loops in the circuit. Here if you consider a loop starting from this point, say N, B, capital A, then A, and completed at small n. That means if you apply Kirchhoff's voltage law equation to this load, so if you start from this point, you can see that you are meeting a rising potential here, which is given by the magnitude of the voltage source. It is given by plus VBN here, and you have reached at this point, and from if you travel the drop across the point capital B and capital A is the product of the current and the impedance. So it will be given by IAB into Z delta, and you can see that you are traveling in a direction opposite to the direction of the current. That means you are meeting a rising potential, and that time will be given by Z delta into IAB. That is the voltage drop across these points A and B, and you can see that there is no drop across this because there is no impedance connected in between the points. And you have reached at this point, and when you travel from A to small n, you are meeting a drop in potential because you are moving from plus to negative. So you get this term minus VAN, and it will be equal to 0. From this you can calculate IAB given by VAN minus VBN. You will get it as IAB is equal to VAN minus VBN divided by Z delta, and we have seen from the previous session that VAN minus VBN will be equal to VAN plus VNB, which will be equal to VAB. So VAB divided by Z delta is the line to line voltage between the points AB, that is the potential between these 2 points, divided by the Z delta, the impedance connected between those 2 points. So by this method we can calculate the phase currents. That means the current flowing through each branch of the load, which is denoted as I capital AB. Here it is IBC and ICA. But the line currents are different from the phase currents. That you can see that the line current is denoted, or it is indicated as I small a. Here the line current in the B phase is indicated as IB, and here it is IC with the small letters ABC. Now, in order to calculate the line current in case of a balanced delta connected load, you can apply Kirchhoff's current law to different nodes. For example, node A, node B and node C. So, if you apply Kirchhoff's current law to this node capital A, you can see that 3 currents are meeting at that point. So, IA, the line current IA is coming into the node, and this phase current ICA is coming into the node, and the current IAB is flowing out of the node. So, if you apply Kirchhoff's current law to this node A, here you can see that if you apply Kirchhoff's current law to this node, you get the equation as IA, because we are considering the current coming into the node as positive. So, you get I small a plus ICA, it is also coming into the node, and minus IAB, which is the current flowing out of the node, and that will be equal to 0 according to Kirchhoff's current law. That is, the algebraic sum of the currents meeting at a point is equal to 0. Similarly, if you apply Kirchhoff's current law to the nodes B and C, you get these equations. Here you can see that IB is coming into the node, and IAB is coming into the node, and IBC is flowing out of the node. So, by Kirchhoff's current law equation, you get IB plus IAB minus IBC equal to 0. And if you apply Kirchhoff's current law to this node, you get an equation IC plus IBC. IC is coming into the node, and IBC is coming to the node, and ICA is flowing out of the node. So, you get this equation IC plus IBC minus ICA equal to 0. And from the first equation, you get IA is equal to IAB minus ICA. Similarly, IB, the line current B in line B is IBC minus IAB, and the line current IC is equal to ICA minus IBC. Now, in order to draw the phasor diagram of the line currents, consider these relations. Here you can see that if the line to line voltage between the lines A and B is given by VAB, which is represented as VL, that is the line to line voltage angle 30 degree. If you consider this as a reference phasor, VBC is lagging with respect to VAB by an angle of 120 degree, and VCA is lagging with respect to VAB by an angle of 240 degrees. And here you can see that the phasor or the phase current IAB is given by VAB by Z delta, and in case of a balanced delta connected load, Z delta or the branch impedance will be same in all the branches. So, IAB will be given by VAB divided by Z delta in phasor form. And you can see that magnitude wise VAB divided by Z delta will be the same as VBC by Z delta. It will be the same as VCA by Z delta. But you can see that IBC will be lagging with respect to IAB by an angle of 120 degree. Similarly, ICA will be lagging with respect to IAB by an angle of 240 degrees because VCA is lagging with respect to VAB by 240 degree and VBC is lagging with respect to VAB by an angle of 120 degree. So, these phases IAB, IBC, ICA can be drawn like this. That means if you take IAB as a reference, IBC will be lagging by an angle of 120 degree. Similarly, ICA will be lagging by a further angle of 120 degree. So, these are the phases representing the phase currents IAB, IBC and ICA. From these relations, you can see that the line current IA is equal to IAB minus ICA. Both these terms are in phasor form or in complex form. And here you can see that IAB minus ICA will be equal to the phasor sum of IAB and ICA reversed. That means IAB plus IAC. And here you can see that IAB is this phasor and ICA is this phasor. So, minus ICA will be the phasor in the opposite direction to ICA. That means ICA reversed. So, you will be getting a phasor IAB is here, minus ICA will be drawn something like this. And if you find the vector sum of this IAB and ICA reverse, the resultant will be this IA. Similarly, IB, the line current in line B or the current in line B is equal to is the phasor sum of IBC minus IAB. That means the phasor sum of IBC and IAB reversed. Here you can see that IAB is in this direction. So, IAB reversed or minus IAB will be in this direction. So, you have a phasor here and you have another phasor, and if you find the phasor sum of these two, you get IB. Similarly, the line current IC is equal to ICA minus IBC. ICA is here and IBC minus IBC is IBC reversed. So, you have to reverse it in this direction and find the vector sum of this vector plus this vector. So, you get it as IC, the line current IC. You can see that the magnitude of the line current is, here you can see that this length of this phasor will be root 3 times the length of this phasor IAB. Or it can be calculated using this formula also. The line current IA is given by IAB minus ICA, which is the same as this. And if you consider IAB as a reference, like this in this phasor diagram, so IAB will be IAB angle 0 and ICA can be written as IAB angle minus 240 degree because we are considering IAB as a reference, and here you can see that ICA is lagging with respect to IAB by an angle of 240 degrees. So, ICA is IAB angle minus 240 degree and magnitude IAB, because you can see that all these phase currents are because it is a balanced load, the magnitude of the phase currents will be same. So, you can take IAB outside and inside the bracket you have 1 minus 1 angle minus 240 degree, and this is using this relation. And here you can see that 1 angle minus 240 degree will be equal to cos minus 240 degree plus j sin minus 240 degree, which can be written like this. And this is equal to 1 angle minus 30 degree. And if you substitute this relation here, so you get IAB into 1 plus 0.5 minus j 0.866, which will be equal to, you can take here, you will be getting it as 3 by 2 and here it will be root 3 by 2. So, if you take root 3 outside, you get here as 1 by 2, inside the bracket you get root 3 by 2 minus j 1 by 2. So, you can see that this root 3 by 2 minus j 1 by 2 is 1 angle minus 30 degree. So, if you substitute this relation here, you get the line current IA is equal to the phase current IAB into root 3. That is the magnitude of the line current, and it's making an angle of minus 30 degree with respect to the reference phasor. That means it is lagging with respect to IAB by an angle of 30 degree. So, this is the relation we have obtained. The line current IA is equal to root 3 into IAB, the phase current. So, this is the magnitude of the line current and it is making an angle of minus 30 degree with respect to the reference phasor IAB here. So the line current IA can be written as IAB root 3. That is the magnitude of the line current will be root 3 times the phase current. And IA will be lagging with respect to the reference phasor by an angle of 30 degree. Here it is to be noted that we have taken IAB as reference. So the line current in magnitude, it will be equal to root 3 times the phase current. And we have seen that the magnitude of the line currents are same in all the lines. So if you indicate the line current IL as IL, it will be equal to IA, the magnitude of IA, which is equal to magnitude of IB, which is equal to magnitude of IC. And IP, if you indicate the phase current as IP, magnitude wise it is equal to IAB, and all these currents IAB, IBC and ICA are magnitude wise equal but separated by an angle of 120 degree each. So from here, if you apply these relations, you get this relation. IL, the line current, is equal to root 3 into phase current. This relation you have to remember. And if it is a balanced load, you can represent it in terms of its single phase equivalent. So for this system, you can represent it in the single phase equivalent form like this. Here you can see that instead of the line to line voltage, here you can see that this is the phase to neutral voltage, same voltage source we have considered here, but the only difference is that Z delta is the branch impedance of the balanced delta connected load. So you have to consider only Z delta by 3 here. And now if you calculate the line current, here you can see that this line current can be calculated using this. That means from this diagram you can see that the current flowing in this circuit will be VAN divided by Z delta by root 3. So VAN is V line to line divided by root 3, and this is Z delta by 3. It can be written as root 3 into VLL by Z delta, and you can see that root 3 into phase current. And here you can see that WLL by Z delta is the phase current, because in between these two you have the line to line voltages. So VLL is the line to line voltage divided by the Z delta. This is the impedance. So here you get as the phase current. VLL by Z delta is the phase current. So the line current IA represented by this single phase equivalent is root 3 into phase current, which is equal to line current from this relation. Actually, this relation is obtained by considering the star equivalent of the delta connected load. We have seen that when we convert from a delta connected load to a star connected load, and in case of a balanced delta connected load, the star equivalent will be obtained by Z delta by 3. So if you convert to this delta load into a star load, you get 3 impedances connected in star here. So the impedance of the each branch of the star equivalent will be equal to the Z delta by 3. And you can see that as we have seen in case of a balanced star connected load, the phase current will be the same as the line current, and it will be obtained, line current will be obtained by the phase voltage, that is VLL by root 3 divided by the impedance in each branch. And in this case of a star equivalent of this delta connected load, the per phase impedance will be Z delta by 3, and that is the relation which we have used here. VLL by root 3 is the phase to neutral voltage divided by the branch impedance of the equivalent star connected load, and from this relation you get this. And this is for just remembering, and sometimes it will be easier to convert into star in order to solve the circuit. Thank you for watching.